Hi, this is your video for section 3.4, which talks about measures of position and outliers. A z-score for a value x is the number of standard deviations that the value x is above or below the mean. And we use the variable x to refer to our data values. So z-scores actually measure the position of a data value relative to the mean and the standard deviation of the data. When a value is greater than or above the mean, its corresponding z-score is positive. And when a value is less than or below the mean, its corresponding z-score is negative. To actually find a z-score for a value x, we subtract the mean from the x value and then divide the result by the standard deviation. The notation is different for a sample than it is for a population, but the two formulas do the same thing. For a sample, the formula looks like this. The x again refers to the data value that we're interested in, the x bar refers to the sample mean, and the s refers to the sample standard deviation. If we have a population, then the formula looks like this. The x still refers to our data value. The Greek letter mu refers to our population mean. The Greek letter sigma refers to our population standard deviation. So for both of these formulas, again, they're doing the same thing. They're taking the x value and subtracting the mean. So here's the mean in this one. Here's the mean in this formula, and then dividing by the standard deviation, which in this formula is the s, and in this formula is the sigma. Now, to interpret z-scores, we want to think about what the z-scores have to do with the x values. So if we look at what happens with the z-score, if our x value is the same as the mean, then our z-score is going to be 0. So both z equals 0 and x equal to the mean are in the middle of our distribution picture. Now if we go one standard deviation below the mean for our x values, we get to -1 for a z-score. If we go 2 standard deviations below the mean for our x value, then our z-score will be -2, and so on. If we're going above the mean, so if we're going 1 standard deviation above the mean, our z-score would be 1. 2 standard deviations above the mean would give us a z-score of 2, and so on. Now, if your z-score turns out to be somewhere between these integers, then that gives you an idea of the placement of the x value on this particular graph. For example, if our z-score came out to be 1.5, which would be about here, that would mean our x value would be halfway between 1 standard deviation and 2 standard deviations above the mean. Now, what this picture is also saying is that what we consider ordinary values are anything with a z-score between -2 and +2. So in this range. And if we're using the empirical rule would tell us that 95% of our values ought to be in between those two places. Now, what we call unusual values are anything outside of that range. So anything that has a z-score less than -2 or greater than +2. Again, if we're looking at the empirical rule, we would have a total of 5% of our values on these two ends. So we'd have 2.5% on this end and the other 2.5% on this end. Let's do an example. So based on information from a survey, the mean height of males is 69.1 inches with a standard deviation of 2.8 inches. The mean height of females is 63.7 inches with a standard deviation of 2.7 inches. So who is relatively taller? Joe, whose height is 81 inches, or Candace, whose height is 76 inches? In other words, if we're comparing Joe just to the male population and Candace just to the female population, who would be relatively taller in relationship to their own population? What we need to do to determine this is to find the z-score for each of the two heights. And the one whose z-score is greater is the one who's relatively taller. So here's our formula. Again, it really doesn't matter if we use the sample formula or the population formula, since they both do the same thing. So for Joe, the x value is 81, the mean is 69.1, and the standard deviation is 2.8. So to find the z-score for his height, we're taking his height, subtracting the mean, dividing that result by the standard deviation, and that gives us 4.25. The rule of thumb for z-scores is that we normally round to 2 decimal places. Now for Candace, the x value is 76, the mean for her population is 63.7, and the standard deviation is 2.7. So for her, again, we're taking her height, subtracting the mean, dividing it by the standard deviation, and we get 4.56. That's rounded to 2 decimal places. If we compare these two z-scores, the z-score for Candace is greater, so she would be relatively taller. Now, another way to think about this is to go back to our scale that compares our x values and our z values. So if we did this for both the men's heights and the women's heights, the value here in the middle, which is the mean, is 69.1 for the men and 63.7 for the women. And then for each one of them, if we go 1 standard deviation, 2 standard deviations, 3 standard deviations below the mean, we get these values, and these are taking the mean and adding 1 standard deviation, or 2 standard deviations, or 3 standard deviations, or 4 standard deviations. And I put the 4 standard deviations above the mean over here because both Joe and Candace came out with z-scores that were more than 4. So their heights would both fall in this area. In fact, Joe's height had a z-score of 4.25, which would put him over here on the z-score scale, and notice that that corresponds to where his height would be on this scale, because it's 81, which is slightly more than the mean plus 4 standard deviations. The same for Candace. Her z-score was 4.56, so her height would be a little bit further over here. And if we look at her height of 76 inches, again, it's a little bit more than the mean plus 4 standard deviations. So the kth percentile, which we denote as p sub k, of a set of data is a value such that k% of the observations are less than or equal to the value. Here's a picture to help you understand this. If we have the very smallest data value over here, then if we're talking about the bottom one, the data value p sub 1 would be the one that would have 1% of the rest of the data values less than or equal to that. So in other words, 1% of the data values are less than or equal to this value. 2% of the data values are less than or equal to this value. And if we went right here in the middle, if we went to the 50th percentile, that would be the one that would have 50% of the data values less than or equal to it. And we could go up here towards the top too. If we looked at the top 2%, that would be the 98th percentile, because 98% of the data values would be less than or equal to that, or in other words, 2% would be greater than this value. Let's do an example. The GRE is a test required for admission to many U.S. graduate schools. The University of Pittsburgh Graduate School of Public Health requires a GRE score no less than the 70th percentile for admission into their human genetics, MPH, or MS program. Interpret this admissions requirement. So if you have to have no less than the 70th percentile on your GRE to get into this school, the 70th percentile is a score such that 70% of the individuals who took the exam scored worse. Actually, that scored the same or worse. So, in order to be admitted to this program, an applicant must score as high or higher than 70% of the people who take the GRE. Another way we could say this is that the individual's score has to be in the top 30%. Quartiles divide data sets into 4 equal parts. So the first quartile, which we denote by Q sub 1, divides the bottom 25% of the data from the top 75%. Since it's dividing at the bottom 25%, it's the same as the 25th percentile. The second quartile divides the bottom 50% of the data from the top 50%. So this would be the same as the 50th percentile. It also happens to be the same as the median, since the median divides the data into 2 halves. The third quartile divides the bottom 75% of the data from the top 25% of the data. So it's the same as the 75th percentile. So here's a picture. We have our list of data from the smallest data value up to the largest data value. And here are our 3 quartiles, Q1, Q2, and Q3. So again, here below the first, the lowest 25%. Between Q1 and Q2, we have another 25%. Between Q2 and Q3, we have another 25%. And between Q3 and the maximum data value, we have another 25%. To find quartiles, we actually use the same process as we do to find the median. Again, the first step is to sort the list from smallest to greatest. Then the second step is to find the median. The median is actually one of the quartiles, it's Q2. So that's one of the ones that we need to find. Now once we've found the median, we use that to divide the list in half. Now we have 2 lists, a lower half of the list and an upper half of the list, and we just find the median of each one of those halves. So the median of the lower half is Q1, the first quartile, and the median of the upper half is Q3, the third quartile. Here's an example. If we have a set of values that were collected on the speed of vehicles traveling through a construction zone on a state highway where the posted speed was 25 miles per hour. If we want to find the quartiles for this data, notice this list is already sorted from smallest to greatest. And there are 14 data values in this list, so to find the median, we will find the average of the 2 middle values. And again, those would be in positions 7 and 8. So that would be the 32 and the 33. So if we average those 2 values, we get 32.5. That's our median. And now we're going to divide the list in half on either side of that. So we've got all the values from 20 up to 32 for our one half, and all the values from 33 up to 40 for our other half. So our lower half looks like this, and we're just finding the median of this list. Since there are 7 values, we can just take the one in the middle, which is 28. So that's our first quartile. The upper half of the list looks like this, and the median would be the one in the middle of that list, which would be 38. So our third quartile is 38. Now again, here was our original list. Our Q1 was 28. Our median was 32.5, so halfway between those two. And our Q3 is 38. So what we're saying is that 25% of the data values are less than or equal to 28. 50% of the data values are less than or equal to 32.5. 75% of the data values are less than or equal to 38. The interquartile range, we usually abbreviate this with IQR, is the range for the middle 50% of data values in a set of data. So the IQR is the difference between the third quartile and the first quartile. We just subtract the two to get the IQR. And again, if we go back to our picture of our quartiles, we're looking at the middle 50% of the data. So from here to here, and that's just the distance between Q3 and Q1. So that's our IQR. So let's go back to our data on vehicle speeds and find the interquartile range. So we already determined our quartiles. Our first quartile is 28 and our third quartile is 38. So to get our IQR, we just subtract those two, which gives us 10. What this tells us is that a range of 10 miles per hour contains the middle 50% of the vehicle speeds. Now an outlier is a data value that's far away from the rest of the values. How can we determine that a data value is an outlier? I'm actually going to give you two different methods for determining this. So the first method uses z-scores. This goes back to what we talked about with ordinary values and unusual values. So outliers are sometimes defined as being more than 2 standard deviations away from the mean, so that they have z-scores either less than -2 or greater than 2. Sometimes we want to define outliers as being more than 3 standard deviations away from the mean. So z-scores less than -3 or greater than 3. The second method uses quartiles and the interquartile range. So outliers can be defined as values outside the fences. And when we talk about fences, here's how we find them. The lower fence is defined as the first quartile minus 1.5 times the interquartile range. The upper fence is the third quartile plus 1.5 times the interquartile range. So outliers are anything that are outside of those boundaries. Here's a sample of 20 employee commute times, and we're going to check for outliers using both of the two methods. So the mean of this data is 19.9 and the standard deviation is 7.4. If we're using the z-score method and assuming that we're going 2 standard deviations below and above the mean as our cutoffs for outliers, then our cutoff values would be, the lower one would be 5.1, the upper one would be 34.7. So notice here I took the mean and subtracted 2 times the standard deviation to get the 5.1. Here I added 2 times the standard deviation to get 34.7. So those are our boundaries for outliers using this method. And the only values, and the values in this list that would be outside of those boundaries would be 35 and 40. There is no value in the list that's less than 5.1, so we wouldn't have an outlier on that end. Now for the other method, we look at the interquartile range. So the first quartile is 15, the third quartile is 23.5. That makes our interquartile range 8.5. And for our fences, our lower fence again is the first quartile minus 1.5 times the interquartile range. That gives us 2.25. the upper fence is the third quartile plus 1.5 times the interquartile range, which gives us 36.25. Notice that these boundaries are actually further out than the ones we had using the other method. So using this method, the only value that would be outside these cutoff values would be 40. So using this method we only have one outlier, whereas using this method we had two.